my name is Allison Groninger, and I'm going to be presenting to you today my project on exploring benzoic acid with a monomembrane in relation to tuberculosis. This is research I've been doing for about a year now in Dr. Krams's lab here at CSU in the chemistry department, and I'm really excited to show you what data we found and how we can apply this data to the world. So tuberculosis, though it may not seem very common in our society today, is actually a really prevalent disease worldwide. It's the second greatest killer and behind HIV and AIDS due to an infectious agent, and there was 9 million cases worldwide in 2013, resulting in 1.5 million deaths. And how tuberculosis works is it's a bacteria that typically infects the lungs, but it can also spread to other parts of your body. But there are drugs out right now to treat tuberculosis, but they usually take about 6 to 9 months to be effective, and this causes problems in that during those 6 to 9 months, people may forget to take their antibiotic or not be able to afford their full dosage of antibiotic, and when you don't take this full course, you may develop multi-drug resistant tuberculosis, which can no longer be treated and results in death. But one of the drugs that we have found that does work in those 6 to 9 months is pyrazinamide. It's a first-line treatment and has been used for over 40 years, and has been shown to work in combination with other drugs. Instead of using pyrazinamide, for my project I used benzoic acid, which is basically the same structure as pyrazinamide minus a couple of nitrogens, but I'm just trying to see how this simple molecule interacts with the membrane, so we can hopefully apply it to this drug pyrazinamide to improve that drug. But benzoic acid also has been shown to treat tuberculosis, and we have found the MIC values, or minimum inhibitory concentration values, in the lab here at CSU in the molecular biology department. And we found that at a pH of 5.5, you only need about 550 micromolars to defeat tuberculosis. But at a pH of 6.5, you need 3,500 micromolar of benzoic acid, which is a large amount, but it has been proven to treat tuberculosis. And how we're thinking this may work is as a protonophore. So the benzoic acid is taking a proton, moving it across the membrane and placing it inside of the TB cell, making it very acidic inside the cell and killing it, and also affecting its ATP synthase, thus allowing the cell to have no energy and it dies. So how we're testing how this benzoic acid is working is on a model cell, and this is a reverse micelle we're using as a model membrane. And my project is to see how this benzoic acid is going inside of the cell. So how this reverse micelle works is it has a water pool, a surfactant, and an organic solvent. And these can be put in a nuclear magnetic resonance structure, or an NMR, and we can see where this benzoic acid is sitting inside of this model cell, depending on how acidic the environment is. So this is the data we get from the NMR, and these peaks represent these different parts of the benzoic acid, so I can see where they are sitting inside of that reverse micelle. The ppm down here, as it gets smaller, shows the benzoic acid going into a more organic environment, or to the outside of that reverse micelle. So what we saw is as the pH decreases, we see these peaks move further into the organic area. And this means that when benzoic acid looks like this and has this proton, it is sitting further into that membrane, while at a lower pH, or at a higher pH, we do not have this proton, and it's sitting further in the water pool outside of the membrane. Overall, we can see from my data that when benzoic acid has that proton, it's sitting further in this organic layer of the reverse micelle, and thus would be sitting further outside of the cell into that membrane and penetrating the membrane. While when it's deprotonated in a less acidic environment, it is not sitting inside of that membrane, it's sitting further in that water pool. This is important to know because now you can see that this benzoic acid is definitely penetrating the membrane, and that is how it is entering the cell. And if we know how this benzoic acid is working, we can apply it to that drug pyrazinamide to hopefully improve it, because we need these drugs to be improved in order to treat this tuberculosis in less than 6 to 9 months, because then we're going to have less of this multi-drug resistant tuberculosis and less deaths due to this disease. Thank you, and I hope you enjoyed my presentation.